This section is going to be about the reaction chart. First, we need to talk about collision theory. Collision theories are when molecules must collide to react. The concentration affects rates because they are more likely to collide if there is more of them there. And they also must collide hard enough. Collisions have to happen, they have to actually happen in general, and then they also have to happen hard enough that they will break apart the other things. So temperature and rate are very, very closely related. And only a small number of collisions actually produce a reaction. So not every time they hit are they going to make a new reaction. So here are some terms for us to know. The most important one, in my opinion, is activation energy. So circle it, highlight it, do anything you need to do. So activation energy is the minimum amount of energy that is needed to make a reaction happen and create an activated complex. An activated complex, or a transition state, this is the more common word I use, is transition state, but it's also known as an activated complex, but are a brief interval of bond distributions and bond formations. So let's talk about this on a given chart. So here we have the potential energy, and here we have the reaction coordination. So we're starting here with the reactions, here with the products, and we're given this huge big slope. The difference between the reactants and this point are what we call the activation energy. So it's the energy required to go from the peak to your reactants, or your reactants to the top of the hill. So how much energy it takes to climb the hill, okay? Once you're to the top of the hill, then the reaction's easy, you just roll on down. Okay, so it's how much energy it takes to go up the hill. The next thing we need to talk about is the activated complex. The activated complex is going to be at this point up here. This peak is what we call the activated complex. Okay, so that's the peak. And then we've talked about these reactions before. We have reactants and products, but we didn't ever look at this huge hill thing in the middle. We just took the difference between the reactants and the products. I'll put this down right here. Let's see if we can draw this. One-handed. Oh, yeah. So the difference between the reactants and the products is, again, our enthalpy, delta H. So let's go back. So the difference between the reactants and the products will be our enthalpy, delta H. In this case, reactants are higher than the products, so this will be an exothermic reaction. Exo. Woo. And that cannot change. The delta H cannot change for a given reaction. The last thing we want to talk about, I'm going to go ahead and switch slides, is when we want to talk about the transition state. Okay, so here's another reaction. We have reactants, specific reactions. We have two bromate nitrates, and you're going to have them, they have to go through this activation. They have to still have activation energy, a certain point, and then they're going to make two nitrogen monoxides and bromine. So let me go ahead and just show you kind of what this looks like. So a transition state is we're going to take, this is what you originally have, is NO. So I'll go closer. You have bromine bonded to nitrate, or nitrogen monoxide. But what's going to happen is when you want to get bromines bonded together, and you want to get the two NOs together. So what's going to happen is there's going to be just a slight bond. So this becomes slight bonds between all of them. This is our transition state, where you have a little bit of a bond here, a little bit of a bond here, and a little bit of a bond here. Nothing's quite broken. They're a little bit less strong, but nothing's quite formed either. So we have just kind of a little bit of a bond between them. Those are what we call a transition state. All right, let's talk about this other scientist. His name, I'm going to butcher it, but it's Arrhenius. And he said the reaction should increase with temperature. Because if you increase the temperature, the molecules are going to have the energy required to get over our great big hill. If they are hotter, they're able to climb this mountain faster. So that's why they said that. And they also say the number of collisions with the necessary energy also increases as well. So you're going to have them moving faster and harder, so they're going to hit the reactions harder and faster, so they were going more likely to happen. So some ways to adjust our chart is by adding a catalyst. A catalyst is going to speed up a reaction without being used up in a reaction. So examples of those are enzymes. Enzymes are biological catalysts. There are two definitions of catalyst. A homogeneous catalyst, which states they are in the same phase as the reactant, so liquid, and liquid is probably the most common. And then heterogeneous catalysts are in different phases as the reactants. Those are going to be solids and maybe a liquid. The most common one here is going to be platinum. Platinum is a very good catalyst for reactions, just so you're aware. So how does a catalyst work? A catalyst allows reactions to proceed by a different mechanism or a new pathway. The new pathway has a lower activation energy. So more molecules will probably take the activation energy. Instead of climbing the huge hill, they'll take the shortcut. But does not change the enthalpy. So let's look here and see how that would affect it. So you're going to still start with this and this. And you want to start here and end here. But instead of climbing this great big hill, you're going to have to climb a smaller hill. So here's our smaller hill. And it's like a shortcut. You don't want to climb this great big huge thing. So you're going to climb a smaller hill to get to your products. So this is what a catalyst does. A catalyst just changes this. It does not change the difference between the reactants and the products. Just how big your hill is. So here's some more examples of a homogeneous catalyst. Homogeneous catalysts could be a chlorofluorocarbons, which catalyze the decomposition of ozone. This is very important because ozone is a very dangerous gas that's causing our atmosphere to heat up. Enzymes also are going to regulate the body processes. This is where they are protein catalysts. This is very important to your day-to-day life. All right, so let's talk more about catalysts. Catalysts can speed up reactions, but only to a certain point. So they can make it go faster. But past a certain point, adding more reactants will not change the rate. So adding more concentration to it will not help. This is what we call a zero-order reaction. More about order later. Make sure you're taking your quizzes.